So we've talked about the first three gas laws, and what we're going to do now is make things a little bit easier. We're actually going to slap these laws together and give you the combined gas law. Here's how this works. Here are the three gas laws we talked about. Boyle's law, the breathing law, related pressure and volume. P1 times V1 equals P2 times V2. When the pressure, the conditions of a gas change from one state to another, if it's just pressure and volume that are going to be flexible, that's how they're related. And that's assuming I keep temperature the same and the amount of gas the same. Charles's law also keeps the amount of gas the same, but instead of keeping the temperature the same, it keeps the pressure the same. Volume over temperature in one set of conditions is equal to volume over the temperature in another set of conditions. Those are directly proportional. As temperature goes up, so does volume, and vice versa. Gay-Lussac's law is also a direct proportional relationship, this time between pressure and temperature, keeping volume the same. So the bottom two, Charles and Gay-Lussac's, they're directly proportional. The top one, Boyle's law, is inversely proportional. As one goes up, the other goes down. But we said that we can combine things, and the combination is very simple. I take one part Boyle, one part Charles, one part Gay-Lussac, and amazingly enough, I've got the combined gas law. The only thing I have to worry about in this case is I'm keeping the amount of gas the same. If I keep the amount of gas the same, this is going to be the relationship for everything else. And a couple of ways to look at it. If I deal with something that is, let's say, the temperature is going to be constant, I just cover up the temperature, and I've got Boyle's law. P1 V1 equals P2 V2. It said the temperature had to be constant. Lo and behold, there's that answer. If instead of that, I am going to be keeping my volume constant, I cover up the V's, and I've got Gay-Lussac's law. Pressure in 1 over temperature in 1 is equal to pressure on condition 2 over temperature condition 2. If it's pressure that I keep the same, I cover both pressures, and I have Charles's law. So that's one of the strengths about the combined gas law. That's the only one I really need to remember. And I can figure out all the others. Whatever I keep constant, I get rid of. The other thing that's helpful is it lets me figure out things when everything bounces around other than the amount. Here's a problem out of your book. A gas on 110 kilopascals and 30 degrees Celsius fills a flexible container, which means you know the volume can change, whose initial volume is 2 liters. The temperature is raised and the pressure is increased. What's the new volume? Well, we always like to think things through before we get started on this, and what do we know about the conditions? Well, we know a couple things. We know that as pressure goes up, we're looking for volume, so we're seeing how things compare to volume. As pressure goes up, and it does, it goes from 110 to 440, that means that volume goes down. That's Boyle's law. We also know, according to Charles's law, that if the temperature goes up, as it does, then volume goes up. Can't really work this through too easily, can we? They're conflicting with each other. In one case, the pressure is increasing, so that's going to mean the volume goes down. But on the other hand, the temperature is increasing, which means the volume goes up. So what's going to win? Well, that's why you need the combined gas law. Now, the first thing to remember, every time you're dealing with the gas laws, you've got to convert it from Celsius up to Kelvin. And you're always going to add 273 to the values. So the values in Kelvin are the ones you need to deal with. Now we've got a little bit better idea. Before I punch anything in, let's take a look at things again. I've got pressure going up, but it's going up fourfold. My temperature also goes up, but it's only going up 50 degrees. We're talking a little bit less than 20%. Not as much of a change. So on this point, I'm thinking pressure is going to win, and we're going to get a smaller volume. But let's find out. Let's put all these things together. Here's my overall setup as far as the equation goes. I'm looking for V2. I can kind of arrange things, pull that all by itself, shuffle the numbers around, And you can work this out on your own if need to. But here is my eventual setup as written in the book. The book likes to keep the pressure and temperatures together. So I got the volume times pressure 1 over pressure 2 times temperature 2 over temperature 1. I start filling in the numbers. There's V1. There are the two temperatures. Sorry, the two pressures, and there are the two temperatures. Work out the numbers. All the units are going to cancel out except for liters, because that's what I'm going to have my answer in anyway. This is a fourfold effect. This is just a little bit more than, well, a little less than 20% effect. That's not going to have as great an effect. You have a final answer of 0.58 liters. Definitely worth working through this problem. Make sure you get an idea, because again, you can't really tell just looking at it initially, especially when it's in Celsius, which way the volume is going to change. So that's a very good problem that's worked out in the book. And here are a couple of other problems that you can work through just to make sure you're comfortable with this. But the key to the combined gas law is you're really putting all three variables and all three laws together that we've already talked about, other than the amount of a gas. And that brings us to Avogadro's principle. I'm not covering this in every class, but in the honors class I'm hoping to cover this, and I'll probably gloss over it with the other classes as well. Avogadro's principle starts to take in the quantity of gas and how it's going to adjust things. Now, you know that different gases have different sizes, individual molecules wise. CO2, you've got these 3 atoms that are involved. Helium, it's a noble gas, I've only got 1. Oxygen and all the other honkelbriefs is going to be just 2 of them put together. So you have different sizes with each molecule. The weird thing is, it doesn't really affect how the volume works. That's one of the keys to Avogadro's principle. If you're at standard temperature and pressure, and standard temperature and pressure is 0 degrees Celsius, or 298 Kelvin, and 1 atmosphere. So we're talking about freezing and regular atmospheric pressure. 1 mole of any gas, absolutely positively any gas, is going to have the exact same volume, 22.4 liters. And this gives you a chance to figure out, you can do some molar calculations. We're not really going to be doing a lot of these. It's just worth noting that 22.4 liters, which is a decent size, that's how much 1 mole of a gas is going to occupy no matter what the gas is, under ideal situations. So that's Avogadro's principle. You can figure out exactly how many particles are going to be in there. It's always going to be the same. And this helps us out in figuring out a couple of other problems that we're going to get into when we talk about the ideal gas law. But it also comes into play with a few different things. And this is one of the problems that's one of the examples noted in your book. The idea of a weather balloon. You don't have a weather balloon totally filled up because it's affected by so many different things. So you put in a certain amount, and that amount isn't really going to change, but you can figure it out based on the amount how it will change in various areas. That's how they figure out how a balloon is going to float to certain levels. Some are going to go to higher levels, some are going to go to lower levels. It's all figured out using these equations. So we're not going to be figuring out this many different things. It's just worth noting that that's the scenario. So this wraps up chapter 14, section 2. And the keys behind this one are these points right here. First of all, Boyle's law, Charles's law, and Gay-Lussac's law can all be put together in the same relationship. P1 V1 over T1 equals P2 V2 over T2. And you just cover what you don't need, or what stays constant. And if there are variables with all of them, there's always going to be one that you can figure out. And the second thing that's worth noting is, according to Avogadro's principle, equal volumes of gases at the same temperature and pressure, specifically STP, which is 0 Celsius and 1 atmosphere, the volume of 1 mole of a gas is going to be 22.4 liters. Good number to remember. Next thing we're going to be talking about is going to be the ideal gas law. We're really probably only going to cover this in honors, and we are not going to cover the real gas law at all this year, just unfortunately ran out of time. But this will be a good primer for going into the ideal gas law regardless.